Okay, here's another example, page 341, number 13a. So what we want to do here is determine if W, vector W, can be written as a linear combination of vector U and V. So we write it out, W equals AU plus BV. Now, unlike the example I did before, this one is in 3 dimensions, so we're going to have 3 equations with 2 unknowns. Okay, so for this one, sub in the coordinates for each one. If we multiplied the A in and the B in, we would end up with these 3 equations. So negative 14 equals negative 1A, this is for the x coordinate, plus 4B. So that's all for the x coordinate. For the y coordinate, we get negative 1 equals 2A plus B. And then for the z coordinate, 16 equals 3A minus 2B. We should know that if we have 2 equations with 2 unknowns, that we can try to solve for one of them with those 2 equations. We have 3 equations with 2 unknowns. So we have, it's like intersecting 3 lines. So these, in order for the A and the B to exist in this one, we need 3 lines to intersect at one point, or be the same line, or to the same line, and the third one intersect at one point. Okay, so intersecting 3 lines, we need there to be one solution for this. Well, we're going to try and find a solution for the 2 of them, so let's use equations 1 and 2. Alright, so if you do elimination with this, 2 times equation 1 plus 2. Well, I didn't write it out in long this time. You can write it out the long way if you need to. But 2 times equation 1 plus 2. Well, let's do each part of it. So 2 times negative 14 is negative 28 plus negative 1. It's going to give me negative 29 this side. 2 times negative A is negative 2 plus 2A is going to give me 0A. So that eliminates the A. That's why we multiplied equation 1 by 2, so that I have a negative A and a 2A to cancel out. And then 4B times 2, well, that's going to be 8B plus B gives me 9B. So 9B equals negative 29, which means B equals negative 29 over 9. Doing the same thing for to eliminate B so we can solve for A, we do 4 times equation 2 minus equation 1. And when you do that, you'll get A equal to 10 over 9. So that's good. There is a solution to the first 2 equations. So we've got a solution. A equals 10 over 9, B equals negative 29 over 9. In order for this to prove that we have an A and B that works for all of them, we need to actually check that solution in equation 3. If it works in equation 3, then the A and the B that we found satisfies all 3 equations and we've got them. If it doesn't work in equation 3, then we can say that they are not linearly dependent. Okay, so that their W cannot be written as a linear combination of U and V. So let's check it here. So we sub them in. So the right side equals, so this is how we check in an equation, right? We do a right side, left side. So right side equals 3 times 10 over 9 minus 2 times negative 29 over 9. Working that all out, you get 88 over 9. And last time I checked, that was not equal to 16, which is the left side. So because it didn't work in the third equation, this A and B that we found does not satisfy all 3 equations. There isn't an A and B that works. Okay? So A and B do not exist, therefore not linearly dependent, and they don't lie in the same plane. These are all things that we can conclude. Okay, so linear dependence mean that one vector can be written in terms of the others. Okay, so W is not linearly dependent on U and V, which means W cannot be written as a linear combination.